Hi, we are the Team 2 of RSS, and for Lab 5, we were asked to implement a localization algorithm. Our problem has three inputs: a map of the environment, the sensor data, and odometry data. And using these three inputs, we are asked to compute an output, which is the current pose of the robot with respect to its environment. And in order to solve this problem, we are using the Monte Carlo localization. The components of our implementation were a motion model, a sensor model, and a particle filter. And by integrating all three components, we achieved the overall Monte Carlo localization. Now our teammates will talk more about each of these components and how we integrated them.
We first implemented a motion model that takes in a list of particle poses and the robot's odometry. Then with that information, we can output the new poses of each particles in that list. To compute this function g, we can't just add the pose to the odometry information, because the odometry, in blue, is given in reference to a previous pose. Therefore, we have to transform the odometry information into displacements in the inertial reference frame, the ones in red. The way we do this is that we multiply a transformation matrix, RZ, to odometry, and then we add it to the previous pose.
We're interested in the spread of the particle rather than its deterministic locations. In order to make the particles to spread out as the car moves, we need to add noise to a model. So to find noise, we sample from the normal distribution. Why normal distribution? Normal distribution because by the central limit theorem, if the sample size is large enough, then the sample means are normally distributed. Therefore, with a large size of sample, we want to use normal distribution to model our noise. At the same time, we want our noise model as realistic as possible. For example, if the car moves in a small distance, then noise would be smaller than if the car moving in a larger distance. To do so, we set the standard deviation of the normal distribution by the magnitude of the odometry times with some factor. And by tuning those factors, we can find the best model for the noise for our motion model.
Now that we've talked about the motion model, let's talk about the sensor model. It updates the particle's likelihood weights, which means that each particle has a probability of being the actual location of the car, and we are trying to calculate that probability. For a LiDAR scan, that's based on 4 different probabilities. First off, the probability that we're detecting a known obstacle, which is what we actually want to do, detect a wall or something that we know about, which is denoted by p hit. Then the probability that we have a short measurement, so this could be due to an internal reflection of the LiDAR or an obstacle appearing, and that's denoted by p short. Next, the probability of seeing a large or missed measurement, meaning that something had a strange reflective surface or for some reason just the beam did not bounce back, and that's denoted by p max. After that, we have the probability of a random measurement, so something just totally random coming into the screen, and we call that p-rand. So we have to scale and add up all these probabilities to calculate the total probability. So first, we look at the probability of a known obstacle, p hit, and we scale that by alpha hit. Next, we look at the probability of a short measurement, and we scale that by alpha short. Then we look at the probability of a large measurement called p max, and we multiply that by alpha max. And finally, the probability of a random measurement is scaled by alpha random. And all of these different scaled factors have to add up to 1 to maintain the fact that the probability should be no more than 1.
So then now that we have all these probabilities, what we can do is we can put them into a pre-computed table, which will make it easier in later steps to look up the probabilities rather than recalculating everything all over again. So as you can see here, this is a 3D version of what the probability table will look like. And what we did with our sensor model was we plotted a 2D version of this to confirm that what we have was correct. So this is our model of ZT and ZT star, where ZT is the measured distance in pixels, and ZT star is the ground truth distance in pixels. And as you can see, this is a similar distribution, except this is from the top down. And when we compare this with our unit test model, you can see that it's a very similar distribution. except perhaps our model is off by some scalar factor. So then the next portion is when we're evaluating, when we get a set of particles and also the LiDAR scan. And what we can do here is we can calculate these particle probabilities by going through each particle. Then within each particle, we look through all the scans, so every beam, and we can calculate this beam probability from the pre-computed table that we created before. And to calculate the overall particle probability, what we can do is we can multiply all these beam probabilities together to get a probability for that specific particle. And we raise this to a squash factor to match with the auto-graded components. So to reiterate, what the sensor model evaluate function does is we take in a set of particles, and we also take in a LiDAR scan, which is a vector of all the positions, and we can calculate basically the probability for every particle and output that.
One of the crucial things that we need to implement for our particle filter algorithm is a way to set an initial guess for the robot position. We use the interactive tool on RViz to set our initial pose estimates and initialize particles with random poses within 1 meter of radius of the point we clicked. The particles are shown in red in this video. With this initial guess, we can start eliminate some unlikely estimates based on the observation from our sensors. The way it works is as follows. It starts with n estimated particles, and then the sensor model tells us the probability of getting each of the n particles. Then we normalize these probabilities. And then we choose n particles randomly based on the normalized probability. After these operations, some particles might be chosen multiple times and some might not even be chosen. And only the particles that are more accurate remain. Then, when the robot moves, we'll want to update the particles' positions as well. After we receive the odometry message, we'll send it to the motion model. And the motion model will tell us the change in position and orientation. We can use this information to update the particle position.
After we update all the positions of the particles, we can then calculate an average estimated pose of our robot. For calculating the average position, we only need to calculate an average value for all the x and y coordinates respectively of all the particles. But for calculating the average orientation, we need to use a formula that helps us calculate a mean value for circular quantities. By plugging in all of our angles into this formula, we get a value that represents an average orientation of our robot. After we compute this, now we can integrate all of our parts. The high-level understanding of our approach is that every time we receive some odometry or sensor data, we update the positions of the particles based on the motion and the sensor models. Then, after the particles are updated, we create an odometry message with a pose that we computed earlier as an average pose. And then we create a transform based on this odometry message, and we publish that transform to the robot, which is the end of our Monte Carlo localization algorithm.